Welcome back. I'm the Tutor Wizard, Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. We're doing the multivariable calculus series. We're in chapter 1, partial derivatives. We are doing section 1.6, which is the directional derivative and the gradient. What are we going to do specifically this lecture? This lecture we're going to do the directional derivative du f x y and the gradient del f x y of a function of two variables, f of x and y. I am ready. All right, now we're going to do directional derivatives. Basically, I'm going to rely on the picture to show what's going on here, and then we'll do some calculations for functions of two variables first, and then we'll talk about the directional derivative for functions of three variables or higher in the next video. Basically, now we've shown you that if we have a function of two variables, we have partial derivative fx and a partial derivative fy. It turns out those are actually the rate of change of the function f of xy at the point x naught. If we have a point x naught, what that is it's the rate of change of our function in the direction of the x-axis, or in particular now we're going to start using some linear algebra, and we're going to talk about vectors in two space, and that's in the direction of the vector 1, 0. Similarly, fy, the partial derivative of f with respect to the variable y, is the rate of change of our function at x naught, y naught in the direction of this vector j, which is in the direction of the y-axis. These ones, in the direction of those vectors. Now what we may want is, this is the idea first before I erase these two guys. What's the idea of a directional derivative? The idea of a directional derivative is if we have, what if I want the rate of change of our function at our point x naught, y naught, but we want it not in the direction of the x-axis, the y-axis, we just want it in any of the arbitrary directions in the plane, in the direction in particular of some unit vector u. And that's what we're going to derive in a second. Let me erase and give us the idea of what we want for the directional derivative. What that's going to say for us is, if I want the rate of change, what we're going to do is pick a point P naught and Q on our curve gamma. What's our curve gamma? Our curve gamma now is the intersection of the vertical plane through P naught and containing the vector u. And that way it's the plane containing the vector, this vector, and that vector. Don't worry, we're going to give, what I'm doing right now is deriving at how to calculate this thing. In the textbooks when they do this, what he's going to do is give a formal derivation of the directional derivative and then magically show that the gradient is involved in this. I would have given the gradient first and then said, here's how I use it in the directional derivative. 6 of one, half a dozen of the other. Let's eat some eggs. What does this give us? If I look at the slope of the tangent line t to the curve gamma, that is going to be the rate of change of z, our function of two variables, at xy now in the direction of u, not in the direction of our x or y axis, in any direction we want. Using the picture now, let's give the derivation of what that's going to be, what a formal definition of the directional derivative is going to be, and then state the definition. All right, quickly, I sort of like the derivation. You don't, so skip over this couple minutes if you just want to see what the definition is, but here's the definition of the directional derivative. I look at these 2 points, PQ, on here. I project them down onto the XY plane, and I get a P prime, Q prime. It's not the derivative, unfortunately, notation. What I now notice is from linear algebra, now we're in linear algebra land, I notice that those vectors are parallel to each other. P prime, Q prime is in the same direction of U, so they're parallel to each other, and that means that what's the Pavlovian reflex from linear algebra? That's correct. It's like you didn't even give me time to answer. I know they're scalar multiples of each other. That's correct. I'm going to use H cleverly instead of T like we do in linear algebra so that the H matches our H in our definition. But if I put a T for the parameter T, it would be f of as T goes to 0, and I wanted H. We've done this before, so I cooked it up. But they're multiples of each other. Now what I do is I view those vectors in two ways, and then that's why I get an equal sign from linear algebra. On one hand, U is AB. If PQ is a multiple of U, that means he's H times AB. And by scalar multiplication of vectors, that goes into every coordinate. So I get HA and HB. On the other hand, PQ from the diagram is x minus x naught, y minus y naught. Hypatia says if two things are equal to a third thing, they themselves are equal to each other. So this is equal to P prime Q prime, and this is equal to P prime Q prime. So this is equal to this, and I get these expressions. This is the change in x, delta x, and this is the change in y, delta y. And because I now have the change in x and the change in y, I can talk about the change in z, my function, or the directional derivative, or the rate of change of z, but not in the direction of the x-axis or the y-axis, the rate of change of z in the direction of our vector u now we built. What does that say? As we let h go to 0 in this expression, we get the definition of directional derivative. Let's do that. The definition of the directional derivative, using the pretty picture to help us, is the directional derivative denoted by du f x naught y naught of our function of two variables at the point x naught y naught in the direction of the unit vector. How do we get a unit vector if I'm given an arbitrary vector? Linear algebra, watch one of our other videos. Divide by its norm. In the direction of the unit vector is, what is that guy? Drum roll, please. Du f x naught y naught is by definition equal to that limit. And then we derived all of those clever formulas. That is the limit as h approaches 0, we were going to say, of the change in z over h, which was what? F of x naught plus ah y naught plus bh minus f of x naught y naught over h. And then I want it to have a fancy, there you go, there's the directional derivative of f in the direction of the unit vector u at the point x naught y naught. And remember, u now, this is why we use x naught y naught. You're like, I like ab, yeah, but now I need my vector to be ab, and so it has to be at the point x. Oh, don't get, you're going to get confused. Let's do an example. Example 1, we want to find the directional derivative of f at 1, 2 in the direction of the vector v, which is 4, 3, if our function is x squared plus y. Coincidentally, a lot of the books do this also. They just talked about our definition of being a unit vector, and then it's like, I took linear algebra a long time ago and I forgot. Technically, you were supposed to remind yourselves in the classes before this what vector calculus was, but just in case, how do I get a unit vector in the direction if they give me just an arbitrary vector? How do you know that this, what does a unit vector mean, remember again? And how do I know this isn't a unit vector? Well, a unit vector, u implies that its length is 1. It has norm 1. And the norm of v is the square root of 4 squared plus 3 squared in a right triangle, which is the square root of 16 plus 9, which is the square root of 25, which is 5, 3, 4, 5 triangle. Either way, what that says is the norm of v is 5, which isn't 1. So not a unit vector. But then the definition I just gave for directional derivative says it has to be in the direction of the unit vector. So we're going to do this first. From linear algebra, given any arbitrary vector v, I can always immediately find the unit vector in the direction of v by scaling it by the reciprocal of its norm. What? V over norm v is how I get the unit vector. Our unit vector now is u is going to be ab in the general theorem. And now who are ab? That is our vector 4 over the norm of v and 3 over the norm of v, scalar multiplied. This is our vector, which is v over norm v, which we just calculated. This is our unit vector. Coincidentally, I'm just trying to match in my brain at first. A is 4/5 in that horrible definition. B was 3/5. There's my two values for my unit vector. Now what do I need? I also noticed that x naught, the point they gave me, is 1. This is the point x naught, y naught. So y naught is 2. Now I have all of the pieces. Those are numbers now. Yay! And we get to put those in there. Now what do we have to do? I also now need to remind myself, what is that derivative? The directional derivative of f at 1, 2 is going to be the limit as h approaches 0 of f of what? It was x naught 1 plus ah 4h over 5, comma, y naught 2 plus 3h over 5 minus f of 1, 2 over h. Now I put them all in. Oh, there's a whole lot of numbers, not letters. H is the only variable. That's why we made it h, not t. Now what am I doing? This is now the definition of derivative, just like in the function of one variable, but now I have to do it for x and y simultaneously, both of the points. What are those, guys? Don't put it in there. Cut the carrots, cut the celery, and then make the soup. What kind of soup only has carrots and celery? Boring soup. Wizard soup. That's what you eat. It's good for your eyes. I need f of 1 plus 4h over 5, comma, 2 plus 3h over 5. And oh, thank goodness I gave myself fairly low degree polynomial in two variables, x plus y. That's going to be equal to 1 plus 4h over 5 squared plus 2 plus 3h over 5. That is equal to, by the binomial theorem, 1 plus 4/5 plus 4/5 is 8h over 5 plus 16h over 25 squared, and then I get plus 2 plus 3h over 5. I also need f of 1, 2, which is equal to what? I'm going to get, this is equal to, 1 plus 2 is 3, but I didn't want to run 3 plus, and then what do I have? 11h over 5 plus 16 over 25h squared. And then this guy is 1 squared plus 2, which is 3. Oh, those are going to cancel. If you've seen my mantra in calculus of one variable, if everything without an h in it better cancel off in the original definition, then we're going to factor h out, and then we're going to push h to 0, and then we're going to get our the rate of instantaneous rate of change of our function of two variables at the point 1, 2 in the direction of the unit vector in the direction of the vector 4, 3. What? Let's put that together now in the definition. All right, by definition, the directional derivative of f at 1, 2 in the direction of the unit vector 4/5, 3/5 is equal to, by definition, the limit as h approaches 0 of f of x naught plus ah, y naught plus bh minus x naught, y naught. In our case, there's all the numbers. We put them in there. We simplify it ahead of time. Now I put it into the machinery. Now we're going to make some soup and stir the pot. First thing I see always is everything without h better cancel, and it does. 3 minus 3 is 0. Good. Now what I have is rewrite it out, and yes, you have to write the limit every time. Limit means limit. You can't just cut off an arm. It's like, close enough. Well, not really. I wanted the whole thing. Don't just start excising things. This gives me 11h plus over 5 times, or plus 16 over 25h squared over h. Also, I don't like writing it like that. You should have written it like dividing by h is the same thing as multiplying by 1 over h. That gives me, what am I going to do with that? I see I have h in both terms. I factor it out. That gives me the limit as h approaches 0 every time of h times 11 over 5 plus 16 over 25h over h. Now it goes away. And for some reason, 1 in 103 people tries to say that that's h over h is 0. No, h over h is 1. That gives me limit again. The limit as h approaches 0 of 11 over 5 plus, I'm not even going to count a common denominator because that one's going to go away, plus 16 over 25h. There is the instantaneous rate of change of that function of two variables at the point 1, 2 in the direction of this vector, or the unit vector. Let's do a theorem now and then redo this question and show you a much faster way of doing this. Okay, now we're going to give a theorem which connects us to, and we're going to have to go back to more linear algebra terminology, and I really start liking this. We start getting partial derivatives of functions in vectors as their coordinates. Let's do the theorem first. Let f be a differentiable function of x and y, then the directional derivative of f exists for any direction u, a, b, which is a unit vector, and we have specifically that the directional derivative of u of f of x, y is equal to fx xy times a plus fy xy times b. I like that a lot. So do you see what I see? Can you see? This is what mathematicians see. If I had some weird vector, oh, a question vector, who is he? I don't know. But if I had him and if he looked like this, I really don't like that either. I like the notation column vector. But okay, the book uses the bra and the cat. And if I had my unit vector, AB, then I definitely notice from linear algebra that the dot product of my question vector, dot product with u, is exactly fx times a plus fy times b, this. And so that says, oh, that's the dot product. The directional derivative in the direction of u is the dot product of u with some other vector. Who's that other vector? That's our next definition. He's called the gradient vector of f. If I have a function of two variables x and y, the gradient is now a vector function of two variables, and those variables are my partial derivatives of f with respect to x and my partial derivative with respect to y. Another notation is, again, from linear algebra. Remember, I and j are these two-dimensional vectors, and so I can write it like this as well. What is that going to do for me? Doing that, I can rephrase the directional derivative. du f of xy is equal to now the gradient vector fxy dot product with my unit vector in notation that is specifically equal to, unwinding it the other direction now. The first direction we had to see, we just derive it as a formula and we had to see, oh, that's dot product. Now that I know it is, let's put that in there. That is the vector partial of f with respect to x, comma, partial of f with respect to y, dot product with AB. And that becomes, by definition of dot product, this times this plus this times this, a times the partial of f with respect to x plus b times the partial of f with respect to y. Let's do that same example and show you that this is a whole lot better way of doing it than using the definition. Thank you, theorem. Not I hate you. Thank you. Example 1 prime, pun intended. So we're going to change number 1 slightly. What am I going to change? Nothing. I'm going to change the method that I use. I'm going to use the theorem, and to make my calculation easier and a direct route in my mind of how I'm going to calculate this hot mess. What do we need? I need to figure out what the point is. The point is 1, 2. I need to find the unit vector again. I did it last time. I'm not going to do it again. Okay, the norm of v is the square root of 4 squared plus 3 squared, which is the square root of 25, which is 5. And then so u is going to be v over the norm of v, which is 1 over 5 times v, which was 4 over 3. And using scalar multiplication, that goes into every coordinate. I get 4/5, 3/5. Okay, I did it again. There's the unit vector. Now I have the unit vector, and I have the point I'm at. What do I have to use? The theorem now, not the definition. Thank goodness. The directional derivative in the direction of u, and u is the unit vector in the direction of b of f at 1, 2. Actually, let's just do this. At xy, at every point now. Why do it one point at a time? Why not compute all of them and then just put in values? This is equal to, by our theorem, it's specifically equal to the gradient vector f of xy dot product with our unit normal vector u. I've already computed u. I need the gradient vector. What is that specifically going to be? The gradient vector f of xy is equal to the partial derivative of f with respect to x, comma, the partial derivative of f with respect to y, which is equal to this guy, to x, comma, 1. In particular, the gradient vector evaluated at 1, 2 is equal to 2 times 1, comma, 1, which is equal to 2, 1, which is a vector 2, 1. Now what am I going to do with that? I'm going to take the dot product of this guy and this guy. Now it's all numbers and we get a number. Yay! Which is going to be, hopefully it's 11 over 5 again. What did that do? That gave me the gradient of f at 1, 2, which I also need, is what? 2, 1. Therefore, the directional derivative of f at 1, 2 in the direction of u is equal to the gradient of f 1, 2 dot product with u, which is the vector 2, 1 dot product with 4, 5 over 3, 5. See, Satan, no more variables. Numbers, which is a dot product of vectors in 2 dimensions. This is 2 times 4 over 5 plus 1 times 3 over 5. And oh yes, we get 8 over 5 plus 3 over 5, which is 11 over 5. That's a whole lot better. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of other ones. I'll see you next time.